This is Astrophysics. This is Surveying the Stars lesson 3, and this one's on apparent magnitude. So first of all, obviously, what is apparent magnitude? Lowercase m, or m. So the apparent magnitude m of a star in the night sky is a measure of its brightness, which depends on the intensity of the light received from the star. So this is basically how bright something appears from Earth. It takes no consideration into how far away it is, which is obviously a big issue. Stars in ancient times were divided into 6 levels of apparent magnitude. So this was about 100 BC. Hipparchus, I think his name was. The brightest were called first magnitude. Those just visible to the unaided eye in the darkest sky were called the 6th magnitude, so 1 to 6. And then moving on, specifically Pogson's law, 1856. So he extended on this work. So in 1856, Norman Robert Pogson defined that the average first star magnitude was 100 times brighter than the average 6th magnitude star. So what this means is that for each change of magnitude, the star's brightness changes by about 2.5 times. On the specification, it's 2.51, but 2.5 will obviously be suffice. And 2.5 times 10 to the power 5 is about 100. So what we're going to do next is some examples of apparent magnitude, because obviously the initial one done by Hipparchus was just 1 to 6. Modern times we've got a vastly different approach. Just an extra bit there, resulting in very few very bright stars. So what we've got now is negative apparent magnitudes. So we'll see that on the examples. So Sirius was a minus 1.47. The sun obviously is extremely bright, so that's the highest, or the highest power output close to the Earth basically. So that's got the lowest apparent magnitude of minus 26.7. Full moon's obviously bright from Earth, so that's minus 12.6. So basically the negative values of apparent magnitude mean that they appear brighter from the planet Earth. So let's do a few questions now. So we're going to do this one. Now you can pause and try this if you like, if you're mathematically very competent. So this one's calculate how much brighter Sirius, which is an apparent magnitude of minus 1.47, is compared with Polaris, which is an apparent magnitude of 2.01. So what you need to do the magnitude difference. So we've got 2.01 minus 1.47, so just add them together. So that gives a difference in apparent magnitude of 3.48. And then for each time you go up 1 in apparent magnitude, the brightness, is about 2.5 times brighter. So what you need to do is 2.5 multiply to the power of, the difference in apparent magnitude. So you got 2.5 to the power of 3.48. And if you put that in your calculator, that'll give you 24.3 times brighter. So this is an important technique. So we'll do a couple of practice questions. It's relatively straightforward once you've been shown it. So we've got 2 more questions to do. All right, let's have a go at this one. So we're going to pause. Right, so star A has an apparent magnitude of minus 2.37. I'm going to compare it with star B, which is a magnitude of 4.48. So we want to know how much brighter is star A. So the first thing we need to do is the difference in apparent magnitude. So it's going to be 4.48 minus 2.37, which gives us a difference of 6.85. And then to get the brightness, we need to use Pogson's law. So 2.5 to the power of 6.85, which is an absolutely massive 532 times brighter. All right, let's do one more. So on this one, which star is brighter? So the negative apparent magnitude will be the brightest. So which one's brightest is star A. And then by how much? So again, we need to do the difference in apparent magnitude. So we've got basically just add them together because one's negative. So you've got 4.52 plus 1.88. Which gives us a difference of 6.4, and then use Pogson's law, application of Pogson's law, 2.5 to the power of 6.4, which gives us 352 times brighter. So star A is 352 times brighter than star B. That should have been relatively straightforward, especially that third one after the two examples that we did previously. So hopefully that's all right. And thanks for watching.